Let's look at total body water and how it's calculated and also understand the concept behind Darrow Yannet diagrams. First, let's look at total body water and how it's calculated. Here, we're going to be using this box diagram to represent the total body water and its components, where the big box, the whole, is the total body water. 2/3 is the ICF or the intracellular fluid compartment, which means all of the fluid inside the cells. And everything else that is not in the cells is the ECF, extracellular fluid compartment, which is 1/3 of the total body water. The ICF compartment and the ECF compartment are separated by the plasma membrane. Furthermore, the ECF compartment as a whole is divided into two, 3/4 of which is the interstitial fluid compartment and 1/4 of which is plasma, which are separated by the capillary endothelium. Now let's look at total body water and its components that we have just discussed. Total body water forms 60% of the body's total weight. And as we saw, it is divided into two, which are the ICF, 2/3, and 1/3 is the ECF. The 1/3 ECF is further divided into two. The 3/4 larger compartment is the interstitial fluid compartment, and the smaller compartment is 1/4 the plasma fluid compartment or the intravascular volume. A few substances are used to measure the volumes of these compartments. Let's look at them and how to calculate the volume of the compartments that we have just talked about. The total body water can be measured using D2O, T2O, and antipyrine. The extracellular fluid compartment can be measured using mannitol, sodium thiosulfate, which is essentially 22 sodium 125 iodine iothalamate, sucrose, and inulin. 4 things. One thing to note here, the ICF compartment cannot be measured directly. So what we're going to do is take the volume of the total body water compartment that's given to us using one of these values and take the ECF volume that has been given to us, and we just subtract the ECF from the total body water, and that gives us the ICF compartment of fluid. Now, the plasma volume can be measured using Evans blue dye and RISA, which is radioiodinated serum albumin, which is radio-labeled iodine 125 albumin. And similarly, the interstitial compartment can be measured by subtracting the plasma volume from the extracellular fluid volume. A few things to note are that the RBC volume can be measured using 51 chromium, 59 iron tied RBCs. Cell volume is 3% of body's total weight and blood volume is 8% of the body weight. Now let's look at transcellular fluid volumes. CSF is 150 ml, pericardial fluid is 50 ml, pleural fluid is 20 ml, and synovial fluid is 1 ml. Here's an equation where we can substitute the values of the substances we just talked about, and the equation is V equals Q minus E upon C, where V is the volume, Q is the amount of the substance or dye injected, E is what has been excreted or metabolized, and C is the concentration after the injection and distribution. So this was total body water and how it is calculated. Let's move on to Darrow Yannet diagrams. The box diagram that we discussed for total body water is the normal Darrow Yannet diagram, where we saw that the whole thing is total body water, 2/3 is ICF, 1/3 is ECF. So naturally, the x-axis is the volume, and here the y-axis is the osmolarity. This was normal. So to understand Darrow Yannet diagrams, there are 3 things that we need to know. The first rule is that osmolarity is the first change. That means this height, the y-axis, is the thing that is going to change the first. The height may increase on hypertonic, decrease on hypotonic, and remain the same when it's isotonic. The second rule to know is that the extracellular fluid compartment is the compartment that is affected first. If we take out fluid, this is going to be the one that's going to be contracted. If we put in fluid, this is the one that is going to expand first. And the third rule is that the ICF compartment is merely reacting to whatever is happening to the osmolarity in the ECF compartment. These were the three rules that we needed to know. Now let's look at what happens when we add or remove hypertonic, hypotonic, and isotonic fluids from the body. For ease of understanding, I've written the three rules that we had discussed here at the bottom of each slide. Let's go on with isotonic fluid and the loss of it and gain. So isotonic fluid is lost in conditions where someone has undergone a trauma or an accident, or essentially where the whole blood is lost. So whole blood loss is a reason. And also isoosmotic volume contraction can happen in diarrhea. Let's talk about what we had discussed, the three main rules that we had discussed. Osmolarity is going to be the first change. So the height is going to remain the same as the normal. ECF is the one that is affected first. Since there's a loss of fluid, the ECF is going to contract. So the ICF is going to remain normal, but the ECF is the one whose volume is going to decrease. And this is the volume contraction in the ECF. And the third change was that the ICF is going to react to the change in the ECF osmolarity. Since the ECF osmolarity is equal to the normal, the ICF is not going to change. So this is called as isotonic volume contraction. Here the fluid has been lost from the ECF compartment, but everything else remains the same. Now coming to gain of isotonic fluid, this can happen in a condition where isotonic saline has been infused to the patient. Again, the height is going to remain the same, rule 1. Rule 2 was ECF is affected first. Since we are adding fluid here, the ECF is going to expand. So volume expansion is seen here. That would be called as isotonic volume expansion. And same as the isotonic loss that we had seen, the third rule, since the ECF osmolarity is the same as normal, the ICF osmolarity is not going to change. So this is what happens when you add fluid to the ECF compartment, the isotonic volume is expanded. Let's move on to situation 2, which is the loss or gain of hypertonic fluid. Now, hypertonic fluid can be lost in conditions where a lot of sweating is seen, where water loss is much more than the sodium loss. So that's basically sweating. Loss is hypotonic. That means a lot of solute is left in the body. That would mean that the osmolarity of the body is now higher than it was before because the fluid component is gone. So the solvent is less and the solute is more. So the concentration is higher now and the osmolarity is going to increase over here. Since we are losing water out of the body, the ECF compartment is going to contract again. And the ICF now is going to react to the osmolarity of the ECF compartment, which has now increased. That would mean that the osmolarity of the ICF compartment now is lesser than the osmolarity of the ECF compartment. It would mean that fluid is going to flow from the ICF compartment to the ECF compartment. So this is the diagram that we are left with. Increased in height and volume has been contracted. So this is basically hypotonic loss of sodium. Now the fourth condition is the gain of hypotonic fluid. Now since we are gaining fluid, the height is going to decrease because the osmolarity of the body will decrease since we are adding a hypotonic fluid. Since the first change happens in the extracellular fluid compartment, the volume is going to increase. The height is going to be less. And since the ICF compartment is going to react to whatever is happening to the ECF compartment, now since the osmolarity of the ECF has decreased and the relative osmolarity of the ICF is going to be higher than the ECF, the fluid is going to flow from the ECF to the ICF compartment. So here we're going to see volume expansion on both sides of the graph, where the ICF also gets more fluid than before and the ECF obviously has more fluid because of the first change. So this is what the complete graph would look like. This is called as overall volume expansion because the volume has been expanded on both sides of the diagram. This usually happens in conditions where someone has drank a lot of water, so excessive water intake can cause overall volume expansion. Let's move on to the last scenario where hypertonic fluid is lost or gained. So in the loss of hypertonic fluid, the first change in the osmolarity is going to be, since the solute is being lost, the height is going to decrease because the body's relative osmolarity is going to decrease. And since the first change is in the ECF compartment, the volume of the ECF compartment is going to be contracted. The height is going to decrease. And now the third change, that the ICF is going to react to the changes that are seen in the osmolarity of the ECF. Now since we had taken away the solute from the ECF compartment, that would mean that the solvent is remaining in the ECF compartment, which would mean that the osmolarity of the ECF compartment has decreased from what it was before. And since the osmolarity relative to the ICF compartment has decreased in the ECF compartment, the fluid is going to flow from the ECF compartment to the ICF volume compartment. That would mean that the volume is going to expand towards the ICF side and contract towards the ECF side. And this is the diagram that we are going to be left with. This is called as hypertonic loss of sodium. Here the loss of sodium is much more than the loss of water. This can be seen in conditions such as Addison's disease or in a patient who has been using loop diuretics. Now coming to the last case, the way this was hypertonic loss of sodium, this case is going to be hypertonic gain of sodium. The same way as the loss counterpart, the gain of sodium is going to be much higher than the gain of water. This can be seen in conditions where bicarbonate has been infused, or also in certain antibiotics that contain sodium. Let's go by the 3 rules for the last time. The osmolarity is going to be the first one to change. Since this is hypertonic fluid, that would mean that the height is going to increase because we're going to add in hypertonic fluid. So adding hypertonic fluid to the ECF compartment first, the volume of the ECF compartment is going to expand, the height is going to increase, and since the ICF compartment is the one that is going to be reacting, the relative osmolarity of the ICF compartment now is decreased with relation to the relative osmolarity of the ECF compartment now. That would mean that the fluid is going to flow from the ICF to the ECF compartment. That would also mean that the ICF compartment's fluid is going to be contracted. The volume of the ICF compartment is going to contract, and that's going to move into the ECF compartment. This is the final diagram that we are left with. Now that we are done with all 6 scenarios, these 3 rules are the only things you need to know. And this normal Darrow Yannet diagram that we had discussed at the very beginning is the one that you need to know. And that's enough to understand all of the concepts that we had just talked about over here. This is written in a neater way so that it's easier to revise. This side of the page is all of the losses, and this side of the page is all of the gains. So the first situation that we had discussed was the isotonic fluid. So I'll just write that over here. The second case that we had discussed was of the hypotonic fluid. And the third one was what happens when we add or remove the hypertonic fluid. And that's all. Thank you.